Hello everyone, my name is Neta. I work at Intel in the Core and Client Development Group. Today we're going to talk about work that was done by me and my co-author Roope Kaivola during 2020. We will describe a novel usage of formal verification, and specifically symbolic simulation, to detect potential data leakage in the process of pre-silicon validation of an Intel Core processor. We all know the importance of hardware security verification. It has become a greater focus area after a few external discoveries of vulnerabilities, and we want to do our best to discover such vulnerabilities internally much earlier, before the project becomes a product. Formal verification has been a focus area at Intel for many years. The infamous Pentium FDiv bug mentioned here showed the importance of covering the full data space to detect corner case bugs. A lot of effort has been invested in over 2 decades to build a verification collateral that will cover arithmetic and logic data paths in formal verification. There are many kinds of formal verification. The method we use for data path verification in the core execution cluster is symbolic simulation, which is the best known method for proving complex arithmetic computation. Today, we will learn how we use symbolic simulation to detect previously unknown potential data leakages in a live project. Before we start, some orientation on the design we are working on. This pretty picture is here to get the idea of scope of work and where we are in the design. We see here a full chip that in this case includes 8 cores. Each core is constructed of basic blocks called clusters, as I will show in a minute, and the one we are looking at is the execution cluster. Now this would look more familiar to most computer engineers, the basic building blocks of a CPU. Of course, in real life, these blocks, or clusters, are slightly different, but the core of the core, the block responsible for arithmetic and logic calculations, is similar. The execution cluster, or in short exe, performs arithmetic, floating point and integer operations, branch misprediction calculations, address generation, and many more. We verify the exe cluster at the cluster level, with hundreds of thousands of flops in the design, and hundreds of thousands of hardware description language code. That is a huge design for formal verification. In this activity, on this huge design, we didn't know where to look for the bugs. We had no prior knowledge of where the risks are hiding. The execution cluster is a pipeline machine. It receives streams of micro-operations, or in short UOPs, as input. It executes different instructions and delivers the results to the write-back. The data space varies from input sources of 8-bit wide operations to 512 bits. Our goal in this activity was to make sure that no secrets are leaking out the cluster perimeter. What are the security challenges in the exe cluster? It is a pipeline machine, which means the write-back data bus is used for all kinds of operations, secret and non-secret. We cannot define a restricted area and make sure nobody reads it. We don't know what a secret is. It is context dependent. In order to save power, many clocks in the design are gated, so it is possible for data to get stuck internally. And another challenge, which was a key goal of this activity, is the undefined space that proposes a risk of exposing such stale data. In an ideal world, in a fully pipelined machine, where all clocks are toggling all the time, we wouldn't have the problem of stale data stuck internally. We know the data flows through the system and cleared every cycle with the next operation coming in. But in the real world, to save power, we cannot let the clocks toggle all the time. The problem is, when shutting down the clocks, it is possible for data to get stuck on an internal latch. As mentioned before, same data path is used for secret and non-secret data. If the stale data hanging there happens to be secret, there is a risk of exposing it by a later operation. How would this later operation read this unexpected result and we wouldn't notice? How come simulation doesn't fail in such a scenario? Of course, this is not the result we expected to read. Well, what if we didn't know what to expect? In some cases, there is no deterministic value expected to be written. For example, if we get a divide operation and the source data that carries the divisor is 0, there is no meaning to the result. So that can be described as a partially undefined operation, because for certain input values, the result is undefined. Other operations are simply defined to write only the output flags and not data. They are fully undefined, because the data result never matters. So if we have no expected result, there is no way to simulate, check, compare to a reference model, generate a failure when you do not know what to expect. But is it true to say that what is written to the writeback bus in these cases truly doesn't matter? Once something finds its way to the cluster interface, it is a potential risk. How can data leak through an undefined operation? Let's look at a simplified example of an output bus that is shared by many operations. One of the operations that can read it has an undefined writeback data. Let's call it UP A, the consumer UP. The data that will be read depends on the operation type. Each operation selects the relevant branch to read, but UP A doesn't write any data and selects default input. So in some conditions, it could potentially read data that was left behind by a previous operation. For example, somewhere inside, there is a latch that was gated by another UP B, the producer UP, for power optimization reasons. The data on that latch can hang there if the latch is not open long enough. If UP B held secret information and UP A can read it, that is of course a security risk. We define the following security property. Every operation is dependent only on the input sources driven at the right pipe stage of the currently operating UOP. So it would not be possible to read information coming from a producer UOP sometime in the past that might hold secret information, whether it was left there a cycle ago or a million cycles ago. Now let's first understand how symbolic simulation works, and then we will learn how it answers these challenges. This is the basic problem of hardware validation of any kind. We have a circuit C, and we want to make sure it satisfies the specification S. We usually build a reference model according to the specification, we run a simulation, and compare. In standard simulation, we drive random values of zeros and ones, and hope to hit enough cases to catch a problem if such exists. To make sure the design is absolutely 100% clean of bugs, we must cover all possible values, which means iterating over 2 by the power of number of inputs to get full coverage. In this case, there are only 3 inputs. So to fully cover this circuit, we need 8 simulations. That's not so bad. But what if we had a 512-bit wide input data, like the width of the source data in the exe cluster? We do not have the time and resources to perform 2 by the power of 512 simulations for each operation of the thousands of operations in the exe cluster. Of course, if you are listening to this video, you probably guessed that formal verification is the solution. And when we talk about handling complex data paths, we use symbolic simulation. Symbolic simulation provides full coverage of data path and hits all cases in a single simulation. Instead of driving to the circuit random values of zeros and ones, we drive a type called symbol. It is a named variable that propagates in the simulation the same way a constant value would. But instead of delivering a constant number to the output, we get a logic expression that represents the function that was generated by the circuit. We compare the function to the reference model, and in a single simulation, we verify the circuit satisfies the specification. Let's take a closer look at how it works. Each bit here is represented by a Boolean expression. Each symbol can hold both values of 0 and 1 at the same time. As the symbols propagate in the circuit, these expressions change according to the functionality. For example, C flips and becomes not C when it goes through a NOT gate. You can see the expression is exactly the opposite of the input. At the end, we get an expression composed by these three variables that represent all possible values of the three inputs of the circuit. This circuit looks a bit more like the execution cluster and performs different kinds of operations. Since our goal is to cover full data space, the sources are fully symbolic, but some control signals are constant, such as the opcode of a specific operation, and valid bits that indicate we are running a valid operation. The clock is also a constant stream of zeros and ones. The symbols propagate along the constant values in the design and produce different kinds of results, depending on the operation. Each bit is a Boolean expression, and each of these expressions would look different. This is what it would look like in a waveform. We have the constant values driven to the control signal, the symbols are driven to the data, and the output result is a Boolean expression. Each bit is a Boolean expression. Notice the values are driven only in the specific cycle when they are relevant for our simulation and the operations pipe stage. In all other cycles, the value is x. Like a symbol, an x can also be 0 or 1 at any given moment, but it is not represented by a Boolean expression and doesn't take memory. In our terminology, that is an uninitialized value, which is an over-approximation of the circuit behavior. So this scenario can represent any given time in the simulation and not just a specific stage in a flow of UOPs. We expect these uninitialized values will not affect the result. When it comes to security verification, they start to matter and have an important role, so remember these for later. Let's go back to the simplified example. We talked about getting a symbolic expression and comparing it to the specification, the reference model. But what happens if we do not have a specification? The symbolic expression holds more information. Since every named variable is in fact a name, we can tell which variables are composing the expression we sampled at the output. In this example, it includes A, B, and C, but it can be a very long list of names. We call that the dependency list. That is a list of names, of symbols that are part of the expression. The dependency list is information we can get from symbolic simulation with absolutely no need to know the logic expression it was generated from. Remember the undefined space? The dependency list tells us what is propagated to the output without knowing the exact expression or the specification. Querying the dependency list and relying on our naming convention, we can tell whether a variable in the list is expected or suspicious. We do not need to know the functionality of the expression at all, just the names of symbols that have propagated there, and these names are meaningful. So how does it all come together? The process of detecting data leakage risks started from identifying the operations that do not have a fully defined write-back result. Then we would run symbolic simulation, which we will do anyway on a weekly basis as the execution cluster is fully covered by our formal verification environment. We sample the output, the write-back, even in cases where it is not defined, extract the dependency list of each operation, and search for red flags. This part is fully automated. We just had to add a thin layer of code on top of the existing mechanism, so we were able to hit interesting cases out of thousands of operations very efficiently. What is a red flag, for example? Something violating our security property, such as a dependency on a variable that is not the sources driven in the right pipe stage of the currently operating UOP. The debug process resembles our day-to-day analysis, tracing back a suspicious variable name and show where it came from and whether that proposes a risk of data leakage. Let's look at the results of this activity. We focused on about 2,000 operations for which the RADBEC databus was relevant. We found that 89.4% were fully defined, so no problem there. But 10.6 had either a fully or partially undefined space. The good news, 97.8% of the operations are okay, either fully defined or they passed our symbolic dependency check. Our analysis reduced the ratio of suspicious operations from 10.6 to 2.2. These 8.4% are undefined, but the effort of finding a specification for these roughly 170 operations and validating them is saved. The remaining 2.2% were all real failures, groups of operations that were mapped to several different risky mechanisms. In a moderate effort of 6 to 8 weeks, we discovered several different mechanisms that propose a risk for potential data leakage, all previously unknown, and we caught them on time. Let's look at a couple of examples of these risky mechanisms. Going back to our shared output example, we are sampling the output of the undefined UOP. When querying the dependency list, we saw that it includes an X. Since X is a non-initialized value, it raised our suspicion because it could hold any data that was left behind by a previous operation. Tracing back where the X came from, we indeed got to a latch that was gated by UOP. UOP is the only run writing to the signal coming out of the latch, and it is gating the clock in a way that it just opens for the one relevant cycle when that specific UOP is using it and then closes. It is possible that sometime in the past, this UOP was dispatched, wrote data to the signal, and that data got stuck there when the clock closed. Most UOPs would not read this stale data because they would write their own result to the writeback. But UOP A doesn't. It doesn't write any data of its own, and it can read the stale data at the output. But any uninitialized signal in the circuit would get the value X. What if our analysis was wrong? We want to show that the data came specifically from this gated latch that holds stale data. So we do a little trick. We replace the X with a unique named variable, one that would not be driven anywhere else in the circuit. Now, if we observe the same name in the dependency list, that is a solid proof that the stale data has propagated all the way to the writeback, and we have a potential data leakage bug. Another example. Remember our simplified example of symbolic simulation waveform? Here it is again. Everything here looks good. The result is composed only of the sources, or named variables, of the currently operating microoperation. Notice the writeback bus is wider than the expected result, because we perform an 8-bit wide operation on a 16-bit wide bus, and the upper bits are not used. Moreover, there is no clear definition of their expected result. But in this example, they are zeroed, so nothing unexpected is written there. But that is not always the case. Here we see an example of an 8-bit operation riding on a 16-bit wide bus. Again, the upper bits are undefined, but here there is no mechanism that zeroes them, and we see an X, an uninitialized value, propagating to the writeback. Where did it come from, and does it propose a risk? We trace it back to a gated latch. Again, we do the trick of replacing the X with a unique name, a combination of the signal name and the time it was sampled, and observe it at the output, which means that the stale data that was there is readable at the interface by the 8-bit operation. Now let's take a quick look at the mechanism that caused this. This logic causes data to linger internally and propagate to the writeback. This signal here is the one we just observed to have an X and replaced with a name variable, source 1 at stage 303. It is used by operations of various data sizes. In our simulation, we drive symbolic values at the full width of the vector, all 16 bits. In this simplified example, we have either 8 or 16-bit operations. In case the operation data size is less than the full width of the bus, the upper bits are gated to save power. For bits 7 to 0, The clock is always toggling, and they are always passed on. But for bits 15 to 8, the clock is qualified with logic that only passes operations of 16-bit data size. Just to clarify, most operations that run on a wider bus than their data size are fully defined. This specific operation was not. Therefore, it was able to read the stale data and also didn't fail in dynamic simulation. It was caught by our symbolic dependency check and later reproduced with constant values. Here is an example of this bug with concrete values as reproduced in dynamic simulation. First, we see a 16-bit operation dispatched at 302 pipe stage, propagate through the internal state at 303, and writes the output at 304. The second operation is only 8-bit wide. It does not open the internal gated clock that only opens for 16-bit wide operations. So the data that was already there is not overwritten or cleared. This same data is what propagates to the output of the second operation and exposes the previous operation's results. The next time this data will be cleared is only when the next 16-bit operation will be dispatched and clear it. To summarize, we worked at the cluster level. That is a very big design. And in a moderate effort, we covered thousands of operations and hit interesting results. We raised the confidence for the vast majority of operations, including the undefined ones that passed our check. The failures were mapped to a few different potential data leakage mechanisms. The details in these examples shown here were all changed or simplified, but they are all real mechanisms we found that were all previously unknown and detected in a live project. We would like to thank everyone who contributed to this activity. Thank you for listening, and I hope to see you in next year's conference in person.